Hello everyone and welcome to the 12th and final tutorial session of the course on compression and fluid dynamics using finite volume method. So in this tutorial I will be going through some revising some of the older the topics that has been taught before and do a few simple numerical some simple numerical demonstrations, and finally I will try to demonstrate how we will go about solving your fluid flow equations using the simple algorithm. Okay, so to begin with, we all started with um, the our simple GST or general scalar transport equation, which is nothing but the temporal term plus del dot rho u phi equal to del dot gamma gradient of phi. So temporal part, this is the convection, diffusion and source, right? And we started and we said that there are different types of partial differential equations, the which can be classified into either equilibrium problems or marching problems, where equilibrium problems are generally of steady state nature, that is elliptical problems, and the parabolic and hyperbolics were the marching problems. So first of all we studied the steady diffusion equation. Sorry. Then the steady convection diffusion equation, then unsteady problems, and finally the fluid flow equations or the Navier-Stokes equations, right? So now let me let's start by doing a sample problem of steady convection diffusion equation and look at all the assumptions and the schemes that we make and how it affects the final solution. And there was also the concept of stability, boundedness, and accuracy, right? We also saw different types of errors that can come up. For example, the the truncation errors, which comes because of the numerical precisions in our computational machines, because our machines will not be able to store infinite number of digits after the decimal points. so it truncates it to a certain precision, and because of this we have sort of a numerical error. And another term is the truncation error that is coming from the numerical schemes that we develop. If you remember from the Taylor series expansion. So for example, if we want phi at I plus 1 expanded over point I, it will be delta x right. And if we just do a simple manipulation, we will have d phi by dx at point I is nothing but phi I plus 1 minus phi I divided by delta x, and it will be order of delta x, right. So this is the truncation error, which appears because we are truncating the higher order terms in the Taylor series expansion when we are designing the our different numerical schemes, right. Okay. Okay, so let us do a sample problem of an unsteady sample unsteady problem. Okay, so let's write down the statement. So a thin plate is initially heated at T initial, let's write it like this. Okay, so we will do a unsteady problem. Okay, so the problem states that there is a thin plate which is initially at a uniform temperature at 200 degrees Celsius at time t is equal to 0, right. So and the temperature at one of the side is reduced to 0 abruptly, and the other side is insulated. And so we will use a explicit finite difference method with suitable time steps to calculate the temperature distribution as we go ahead in time. Okay, so let us draw a schematic of the problem here. Okay, so this is x equal to 0, which means it's insulated, and the right end is kept at t is equal to 0 for time greater than 0. That is just after we start our experiment, the temperature at the right hand side and right hand side boundary abruptly goes down to 0, and we have the T initial is nothing but 200 degrees Celsius, or we can just take Kelvin for our convenience. Okay. So what will be our governing equations? So governing equation will be just the 1D transient heat conduction equation. Let's write it down. It is rho c dou T by dt okay, and okay, I have already written it down. So at the boundaries, what will be the initial conditions is there, but what are the boundary conditions? So T at x equal to L, that is this boundary, will have temperature is equal to 0, right? And at the right end, that is T at x equal to 0, what do we have? We have insulated end, right? So which means that the heat flux is 0, which also means that the q dot, which is proportional to the dt by dx, so we can say that the dt by dx equal to 0 okay. So we do not have a boundary condition for T, but for the derivative of the temperature, right? So we have here the Dirichlet boundary condition and Neumann boundary condition. Okay. So we have our initial condition and our boundary condition ready. Now we will be able to solve this problem. And also this problem has an analytical solution, because and we can compare our numerical results with a numerical solution and see how the different time stepping methods or schemes affect our final numerical solution. Okay, so since we are using an explicit scheme, we only get we do not get a system of linear equations. Okay, we do not get a system of linear equations, but we just get simple independent equations, which can be algebraic equations, which can be solved not solved, which can be we just put the value and get the values we need, right? So now the governing equation So we now divide our domain into say four cells. So if we divide our into four cells, and say we have a length of say 0.4 or 5 cells, so we'll take a length of say L is 2 centimeter or 0.02 meters, and say we have n or the number of grid points as 5. So we have delta x is equal to 0.02 divided by 5 is nothing but 0.004 meters. Okay, and we need the value of k. Let's just keep it as it is for now. Okay, so the first term will be Tp1 minus Tp naught by delta T. So let me write it down. So this 0 superscript is a superscript, right? It's not power. The 0 superscript denotes previous time step value, and this denotes so this is the unknown, right? This is the superscript 1 will be unknown, and superscript 0 will be the known value, which is the value at the previous time step. Okay, so the first term has been discretized. Let us write it down here. This is with the this is after we do the Gauss divergence theorem, then we get the gradient, then linear profile assumption, and finally we get this kind of a form. Okay, now that we have this okay, these so for the cells, so this is our domain. So for 2, 3 and 4, so for cells 2, 3 and 4, this will be the equation. So rho C Tp1 minus Tp naught by delta T K times Te. Okay. All right. So what about the point number 5? The right side boundary, we always have the T temperature as constant. So okay, yeah, so this is for the interior points. So let me just, this is for, so for the interior points, points 2, 3 and 4, we'll have both the neighboring cells, right? So we'll have T east and T west as well. So what we can write is, this is the for the east boundary, and for the west boundary we can this will be minus k times Tp naught minus Te naught Tw naught divided by delta x. Sorry. But what about the two boundary points? So let's write for them as well. For cell 1, what do we have? We have dt by dx at the this is the west boundary, right? At the west boundary is 0. So we will be only left with the east boundary diffusion flux. And this term will become 0, right, because of the insulated boundary condition. What about the 5? So it will be sorry. So in the west phase, we do not have anything beyond the west face, right, because this is the boundary and t is given as 0. So the only difference will be, so t t sorry, this is east, t east small e minus tp naught and the distance will be half of delta x, right, because and the same old thing for the west face. Okay, and this te is 0, so we'll just write it like that. Okay, so let's now write this in the familiar form of okay. mm, okay, so let's just write the this as tb for t boundary to be consistent. Now we have we have to define what is AP, AW, A east and SU for the different cells, right? Different nodes. So let's write them down. Okay, because 1 and 5 nodes will have some different values compared to the interior points, which are 2, 3 and 4. So in the node 1 there is no west neighbor, right? No, node 1 does not have a west neighbor, that is why the AW will become 0. The A east will be k by delta x, and these will be all k by delta x. And similarly in the fifth cell, in the fifth node there is no east neighbor, so a east will be 0 and a west will be k by delta x. And what else is there? Let me just see. So for point 1 and for the interior points, there will not be any extra terms, extra source terms, right? So the source terms will be 0 for node number 1 and node number 2, 3 and 4. But in node number 5, if you see yes, node number 5, if you see, we will be encountering this term, this whole term, which will get absorbed in the source term. Okay, so if you are having any issue, I will okay, yeah, I think no one is there in the call. Okay, so I'll just expand this term and show you how the source term is getting absorbed. So rho c equal to k by delta x by 2 TB minus TB naught okay, there will be a case rho c k by delta x okay. So now that we have this form, let us write like this. So rho c delta t what about the tw? This only has this term, so k by delta x. What about east? There is no east term, so we have to now take care of this TP naught. let's bring this TP naught to the right hand side, which will be rho C delta T minus of K delta X plus SU, which is nothing but this term. Okay, so what do we have finally here? So rho C by delta X, sorry, delta T okay, I think I forgot one part. There will be a volume integration as well, and since it is a 1D problem, the volume will be just delta X. So we have rho C delta X given as AP naught, or okay, not AP naught, it's only AP, and so now we can write it as AP TP1 is equal to A west T west naught plus A east T east naught plus AP plus AP minus of A west minus of A east, and a TP naught plus SU. Okay, so if we compare this form with the previous line, we can get that for node 5 we have A east is 0, and finally we have SU as 2K by delta X TB minus TP naught. Okay, sorry. Now in the so for a solution to be bounded, we saw that all the coefficients should be of a positive value, right? So but here we see that we have a value of AP minus AW minus A east, which might go to 0. So we give a condition that it should be greater than 0. We reached at this conclusion from both ways. First, we did this in terms of showing that the solution to be bounded, we need all the coefficients of the neighboring cells to be positive, and we also did something called the von Neumann stability analysis, which also gave us a similar conclusion, not similar, the same conclusion, that that dictates the delta t, or the time stepping that we are allowed to choose for explicit time stepping methods. Now if we do that, and AP is nothing but rho delta x by delta t, rho c times c, and it is minus k by delta x. It will be 2 times of that. So it should be greater than 0. Now if we look at it, so we will have let's take the delta t to the right hand side and flip it, so it will be rho delta x okay, let's just rho delta x times c by delta t should be greater than equal to so should be greater than should be greater than equal to maybe 2k by delta x, or we can finally have so 2k by delta x should be rho delta x c by delta t. So we'll take t to the right and left hand side, so delta t is less than equal to should be less than equal to rho delta x whole square c by 2k. Okay, so now let us assume some values for c delta x. So delta x we already have, it is nothing but 0.004 or 4 millimeter, and rho let us take as 10, c the specific heat to be 10 to the power 6, and the thermal conductivity to be 10. So this becomes, so our delta T should be less than or equal to 10 times 0.004 whole square times 10 to the power 6 divided by 2 times 10. Okay, so delta T should be less than okay. So to achieve a stable solution, we need to have a delta T value of less than 8 seconds. Okay, so let us take the delta T value to be 2 seconds. So what will be our k by delta x? It will be 10 divided by 0.004 . What about our AP? Rho c delta x by delta t, 10 times 10 to the power 6 times 0.004 divided by 2, right? So 10 to the power 3, let's get it 20, 0. Okay, so 20 20 times 1000 is equal to 20,000. Okay. Let us look at, this is AP, right? This is A East and A West. So for node 1, the equation will be 20,000 times TP1. Just check. A East is okay and A West is 0. Okay, so we finally have, we'll just cut the 2 zeros everywhere. What about node 2, 3 and 4? It will be 20,000 TP naught, 2500 T East plus 2500 T West minus which is 0. So finally it becomes 200 TP naught equal to 25 T East naught plus 25 T West naught plus this would be 150 TP naught, yeah, okay, and so node 1 TP tp1 equal to okay, I think we have done for node 1. Node 5. So in node 5, there is no east neighbor, so only west neighbor will be there. So west neighbor is 2500, and what else was there? There was a source term, that is 2k by delta x tb minus tp naught. K by delta x, what is k by delta x? Is 2500, tb is 0 minus tp. Alright, so we have finally and we'll have from here 5000, so totally it becomes 7500, and tp naught, and finally we can write 200 tp1 equal to 2500 t west naught plus, sorry, not 2500, it will only be 25 t west naught plus 125 tp naught. Okay, so we have these three sets of equations. Now we can now we can easily get all the solutions at different times, because so let's write it down. Two seconds, what will we have? So for, okay, let me just write all the equations together. So at time t equal to 0, everything is 200. At t equal to 2 seconds, we'll have for grid point 1 t100 1 by 200, so it will be 1 by 200 times 25 and 175. Okay, 25 times 200 plus 175 plus 200. Okay, similarly for node 2 it will be 1 by 200 times 25 times 200 plus 25 times 200, and what is the what plus 150 plus 150 times 200. Same thing here, same thing here, and what about this? It will be 1 by 200 times 25 times 200 plus 125 times 200. Okay, so these comes out to be this is how much this comes out to be 200. This also will come out to be 200. Similarly this one, but here you will see this will come out to be 150. So at time t is equal to 2 seconds, we see that the point which is in the right side boundary, near to the right side boundary, where the temperature abruptly goes to 0, the temperature falls from 200 to 150. And as we will go ahead doing substituting the new values, we'll see that, for example, in the next time step, if we look at point number node number 4, so the equation will be something like 1 by 200 times 25 times 200 plus 25 times 150 plus 150 times 200, and this will again result in a less temperature. So in the next time step, in time t is equal to 4 seconds, we'll have the temperature as 193 point something, and this will go further down 118 point something, like that. So as you see in this transient problem, as we go ahead in time, the temperature profile changes at each time step. So initially it was say this is 200. Initially it was a 200 degrees Celsius. Then suddenly it went to 0. So let this be 0. So this is the boundary. This is 0 0.1, 0 0.2, 0 0.3, 0 0.4 and 0.5, and let this be the boundary. This is at time t is equal to 0. At t is equal to 2 seconds, these will all be same, but this will go down to some value. This is 150, and this is a t is equal to 2 seconds, and then again for t is equal to 4 seconds. And similarly it will go down as we progress in time, and finally it will have a shape something like this at say t is equal to some large time, when we have let the solution to evolve for a more amount of time. Okay, so this was an example problem of a transient sort of problem, and when we take that delta t of greater than 8 seconds, for example if we take 10 seconds, and then we will see some numerical oscillations that is coming up. For example, if we take it as 8 seconds, the solution will become something like this. It will become unbounded and unstable. Okay. So I will encourage you to do the same thing for a explicit method for a higher time step, and take that time step and use it for an implicit method. You will see that the solutions will nicely converge. Okay, so now we will go ahead and do a problem in the simple using the simple method. Okay, just give me 5 minutes, I'll be back.
Afghanistan captures Pakistan's tank.
Okay, so now that we have covered the uh, mm, transient problems, let's quickly go through the simple algorithm, and I'll again explain to you how this simple algorithm works, and other different variations of simple algorithm called the simplex or the piso algorithm and the simpler algorithm. Okay, so the simple algorithm gives a method for calculating the pressure and velocities, and the method is iterative. Okay, so just to give you a brief overview of what we had covered in the simple algorithm. So it converts the continuity equation to a pressure correction equation. So first we took a guess value for the pressure and velocities, which is denoted by the superscript star, E star and U star, V star and W star. Okay, then we solve the momentum equation. Yeah, so we solve the momentum equation using the guess values, and if you remember, we had to do something called staggering of the grid, which means that we will store the pressure, density, the gammas. Let me just briefly touch upon that again. Just a moment. खुला खुला आई इधर So we store the velocities in the staggered grid. This is to avoid the avoid the checkerboarding patterns where we get a zero pressure gradient even when there is an uneven pressure distribution, right? So when we store the velocities in the staggered grid, then we solve for the velocities in the staggered grid, and we get a new velocities which satisfies the momentum equation. So so we get an improved gas value of u, v and w, which are u star, v star and w star. And after we get the new values, then we solve for the pressure correction equation using these new improved gas values, right? We solve okay. So now we have the pressure correction term. So once we have the pressure correction term, we will correct the pressures and at each grid point, and also the velocities at each grid point, which is given as P capital I capital J is nothing but P capital I capital J star, which is the initial gas value, plus the P prime capital I capital J, which is the correction term. So once we do the pressure correction, then we will go ahead and do the velocity correction, which is nothing but u small I capital J 1 and j minus p prime capital I capital J. And similarly for the v, v capital I small j is equal to v capital I small j star plus d capital I small j times p prime capital I capital J minus 1 minus p prime capital I capital J. Now that we have corrected the velocities and pressure, we will compare these values with their previous iteration values. So we'll then, if the error comes out to be less than the tolerance, which we might give depending on the problem, how accurate do we need. So for example 5 decimal places, 6 decimal places, or 8 decimal places. If it is satisfying, if it is yes, then solution is converged, and if no, the solution not converged, and we take these existing values as the guess values for the next iteration. So as you see, the simple method is a guess and correct iterative method, and it generally takes 2 to 4 iterations to converge at the desired solution. Okay. So here we developed this algorithm using this pressure correction written in terms of the velocity guesses, and if you remember, we did a simple approximation that we while deriving the pressure correction equation, we did a simple assumption, and we neglected one of the terms. This gave us the simple algorithm, but there is another variation to that, which is called the simpler algorithm, called SIMPLE and R, simpler. This R stands for revised. Okay, so this is the revised simple algorithm that was also developed by Patankar, Suhasbi Patankar, in the 1980. Okay, so it is an improved version of the simple algorithm. So in this algorithm, the discretized continuity equation is used to derive the discretized equation for pressure, and instead of the pressure correction equation in the simple algorithm. Okay, so the intermediate pressure field that is obtained directly without the use of a correction. The velocities however that we obtain through the velocity correction is same as what we do in the simple algorithm. So the discretized momentum equation, let me write it down. U small I capital J, A and B, U and B plus B small I capital J divided by A small I capital J plus A I small I capital J divided by A small I capital J times P capital I minus 1 capital J minus P capital I capital J. Okay, and similarly we'll have the terms for the V velocity. Let me write it down as well. Capital I small j equal to summation A and B V and B plus B capital I small j divided by A capital I small j plus A capital I small j by A capital I small j P capital I capital J minus 1 minus P capital I capital J. So in the simpler algorithm there is something called the pseudo velocities. Given by a hat U small I capital J hat A and B U and B plus B small I capital J divided by A small I capital J, and now in terms of the pressure correction we can write it like this. We can write the new velocities, U velocities, as U is equal to U hat I small I capital J plus D small I capital J times P capital I minus 1 capital J minus P capital I capital J, and similarly V capital I small j is equal to V hat capital I small j plus D capital I small j P capital I capital J minus 1 minus P capital I capital J. Okay. Now if we introduce these relations in the continuity equation, which is nothing but rho A U, say at the east face, minus rho A U in the west face plus rho A V in the north face minus rho A V in the south face. This is the continuity equation, and we now just replace replace the relations that we have developed. So this will come out to be rho small I plus 1 capital J A small I plus 1 capital J, and this will be U hat small I plus 1 capital J plus D I plus 1 capital J capital I capital J. Okay, now for the V velocities, it will be rho capital I small j plus 1, A capital I small j plus 1, V hat capital I small j plus 1 plus D capital I small j plus 1 times P capital I capital J minus P capital I capital J plus 1. And finally the last term, rho capital I small j A capital I small j V hat capital I small j plus D plus D capital I small j, and the pressure will be P capital I capital J minus 1 minus P capital I capital J. Okay, so now that we have this, we can then simply arrange it in terms of the pressure and not the pressure correction. Okay, so we will have something like this. So we'll have A capital I capital J, P capital I capital J is equal to A capital I plus 1 capital J, P capital I plus 1 capital J plus A I capital I minus 1 capital J, P capital I capital minus 1 capital J, and so on. So and we have A capital I capital J is A capital I plus 1 capital J plus A capital I minus 1 capital J plus A capital I J plus 1 plus A capital I J minus 1, and so on. And what will be the values of this? These are, so A, for example, A Ij is nothing but rho d A capital I capital J, sorry, and so on. And finally the B capital I capital J will be rho u hat A small I capital J minus rho u hat A small I plus 1 capital J plus rho v hat A capital I small j minus rho v hat A capital I small j plus 1. Okay, so these so you have to note that the coefficients of this equation, the coefficient of this equation are same as those as the pressure correction equation that we have derived for the simple algorithm, right? Okay, so the difference is that the source term B is using the pseudo velocities instead of the gas velocities, the u stars and v stars, right? So the only difference is uses the u hat and v hat instead of right in the simple algorithm. Okay, so in the simple algorithm what we did, it is we got the velocities, from the from solving the momentum equation using the guess values of the pressure field, and then we did what we did is with those guess values we solved the pressure correction equation, and then we solved the pressure. But here there is no pressure correction equation as such. We directly compute the pressure field using the pseudo velocities, or the pseudo velocities u hat, v hat, w hat, using these equations. Okay, so what do we see here? We see here that the pressure term is absent from these pseudo velocities, and as a result we do not have to guess for the pressure values, and we can straight ahead go and solve for the velocities, and then we'll use those pseudo velocities to finally compute the pressure field. Okay, now there is another variation of okay, so there is another variation of the simple algorithm called the simplex algorithm. Okay, so here the C stands for consistent. Okay, so it was introduced by Van Dormal and Raithby in 1984. Okay, it follows the same step as the simple algorithm, with the difference that the momentum equation is now manipulated so that the simplex velocity correction equation omits terms that are less significant than those omitted in the simple algorithm. So if you remember, in the simple algorithm we neglected some of the terms, and in the simple algorithm we neglected some of the terms in the velocity correction, but here we will not do that, right? So what is the major difference here? So so if you remember, in the simple algorithm so in the simple algorithm, for example, we have this discretized momentum equation, u prime momentum correction equation, to be precise, a n b u n b prime plus p prime capital I minus 1 capital J minus p prime capital I capital J times a of I small I capital J, and we said that the u prime small I capital J is nothing but d small I capital J of p prime minus p prime capital I J, and where we said that the d small I capital J is what it becomes a small I capital J by a small I capital J, and this is for the simple algorithm, remember. And but what happens in the simplex algorithm is that so u prime small I capital J is d small I capital J p prime capital I capital J capital I minus 1 capital J minus p prime capital I capital J is the same as what we had in the simple algorithm, but the subtle difference is the d capital small I capital J is now treated as is now written like this: a small I capital J minus summation of a and b. Okay, so similarly we do the same thing for the velocity correction. So in the discretized pressure correction equation is the same as what we had done in the simple algorithm. So except for the d term, the calculations of the simpler and simplex and simple algorithm are all the same. Okay, let me just make the final comment here. So in the simplex algorithm, everything is similar to what we do in the simple algorithm, but the only difference is that the d term that comes up in the velocity correction equation, the velocity correction equation that we derive, the only difference is the d coefficient that we compute involves an extra term. That is the only difference. Okay. Now finally I will just show a I will just go through the piezo algorithm, which is another important algorithm called a pressure implicit with splitting of operators. This is an algorithm which is used for pressure velocity calculation for this is sort of a non-iterative computation for unsteady compressible flows. Okay, so this was first developed in this for this regard. Okay, so it's called the piezo algorithm. One moment. Okay, so it was developed in 1986 by ISA, and it was originally uh, developed for unsteady computation of compressible flows. Okay, and it has been subsequently successfully adapted for iterative solution of steady state problems as well. So the piezo algorithm, the main difference is that it involves one predictor step and two corrector steps. Okay, so instead of one corrector step, the piezo algorithm involves two corrector steps, which is contrary to the simple algorithm where we only do one corrector step. So it is just an extension of the simple algorithm with a correction with an extra correction step, right? Okay. So what is the predictor step? So the discretized momentum equation are solved with the guess intermediate pressure fields to give the velocity components, which is same as the um, same as the simple algorithm. Discretized so discretized momentum mm, mm, the discretized momentum equation is solved. This part is same as the simple algorithm. Okay, now there is a character step. There are two character steps. The first character okay, so let me just give you the whole the flow chart for the piezo algorithm. And then we perform the same steps as we did in simple algorithm. We solve the discretized momentum equation, then solve pressure correction equation. So we get u star, v star and w star. We get the p primes. Then we correct the pressure and velocities. Then we get a new set of variables p star, u star, v star and w star. Then we solve for the second pressure correction equation. Then we again do another correction step, and we get the final or the intermediate velocity and pressure fields. Then we again do the same thing, that we check for the tolerance, whether the solution has converged or not, and if it has converged, then we stop the iterations, and if not, then we go ahead and use these values as initial guess, and we start from the top and do the whole thing again. Okay, so this has been found to save computational effort due to improved convergence due to the extra correction step. Okay, so the improved procedure simpler uses the pressure correction to obtain the velocity correction only. A separate, more effective pressure equation is solved to yield the correct pressure field. And since none of the terms are omitted in the discretized pressure equation, the simpler algorithm results in a pressure field which corresponds to the velocity fields in a much better way. Okay, so therefore the simpler algorithm, the application of the correct velocity fields results in a correct pressure fields, whereas this is not the case for the simple algorithm. Okay, so just to give a brief summary, uh, there has been multiple improvements on the simple algorithm. So there has been multiple refinements to the simple algorithm, which has been much more stable. So simple algorithm with the simpler and the simplex algorithm, and the steady state piezo algorithm adds an extra correction step to what we were doing in the simple algorithm to enhance the performance per iteration. So at each iteration the convergence rate increases. Okay, so and another important thing is the under relaxation. So when we correct the pressures and the velocities, we generally tend to under relax it. That is, we multiply the correction with some alpha where the alpha value is less than 1. This is to ensure that the iterative method is stable. Okay, so under relaxation is done to okay, so we have covered all the pressure, velocity, coupling algorithms that are being used in the CFD community, and we see that this is because of the fact that we do not have a transport equation for the pressure. So we make a compromise, and we create a pressure correction equations in terms of the velocity gas fields, and convert the continuity equation into a pressure correction equation, and this helps us solve this issue of the unavailability of a pressure a transport equation for the pressure. Okay, so I think it's time. I think I'll stop now. Thank you.